Hello everyone, welcome, and as you can see, today's topic is projection. This word is pretty familiar to most of us because we use this word in our daily lives, so we kind of already know what it means. But in a more formal way, projection can mean slightly different and specific things in different specific fields. So today we are going to talk about that, and we're going to see what it means in the field of linear algebra. So let's not get too formal at the beginning. So what do you mean, or what really comes into your mind when you think of the word projection? Well, in computer graphics, for example, projection basically means the mapping, or you know the representation of a three-dimensional object. Let's say this is a three-dimensional object uh, onto a two-dimensional surface. For example, your computer screen, you are watching 3D objects in a 2D screen, right? So you are not actually watching something 3D. You are watching a representation, a two-dimensional representation of that 3D object. For example, when you are watching a football match, the football in itself is a 3D object, but on your screen, it's just a circle. So the projection of that three-dimensional football on your two-dimensional screen is a two-dimensional circle. So that's what projection means in computer graphics. In mathematics, however, projection is defined more generally as something, a mapping from a set to a subset. So I have a set and let's call it A. I have another set which is a subset of A, so let's call it subset of A. So the projection is a mapping from A to its one of its subset, so that the operation, this mapping, is idempotent. What do I mean by idempotent? Well, we have come across this term before. Idempotent. Idempotent. An operation is called idempotent when, if you perform that operation multiple times, it gives you the same result as if you perform that operation one time. For example, let's talk about projection. So one very popular and real-life example of projection is, let's say, so you are mapping, so let's say the shadow of an object, right? So this is a three-dimensional object, this is a piece of paper, so we have let's say we have light coming from that direction, right? So we are going to get a shadow of this, right? So this is a projection. The projection of this 3D box on this 2D paper is this two-dimensional shadow, right? Now if you project the shadow one more time onto this paper, you are going to get the shadow. So the projection, let's say this point, the projection of this point on the paper on that same paper is that point itself. So if you project this shadow one more time or three more times or 300 more times, you are going to get this shadow. So performing the projection more than one time is getting you the same result that you got from performing that projection one time. So this property is called idempotent. And similarly, in linear algebra, we have projection defined as follows. Give me a minute. So in linear algebra, projection is actually defined as a linear transformation. So we have a vector space, let's call it V. So a linear transformation from V to itself. So the transformation, let's call it P. Okay, so the transformation P that goes from V to itself, so that any higher power of P is equal to P. So P square is equal to P. P cube is equal to P. Basically, P square equal to P gives all the higher powers. because p cube is basically p into p square, which is p square is equal to p, so p into p, which is p square, which is equal to p. So anyway, so that is the definition of projection in linear algebra: a linear transformation from a vector space to itself, so that p square is equal to p. So this is the idempotent property that we're talking about. So let's say we have a vector x, right? So if we apply this transformation, we multiply x with p, we get something. Let's say xp, the projection of this vector. So according to this definition, if I apply this transformation one more time, so p square, so if I apply the same transformation on the projected vector, I will still get the projected vector, right? So this is the definition of projection according to linear algebra. Let me summarize. So in linear algebra, a projection is a linear transformation defined, let's call that linear transformation P, defined from a vector space to itself. So the projection or the transformation is going from a vector space to itself. So the mapping is from the space to itself, so that the property that has to be satisfied is the transformation is idempotent. So if you apply that transformation more than one time, you'll get the same result. And this is true not only for p square, it is true for any higher power. So p to the power n, where n is greater than 1 and n is an integer, we get Pn is equal to p, which means if you apply this, let's say we have a vector, if you apply this projection on this vector, you get the projected vector. Let's call it xp. According to this condition, if you apply p to the power n to this vector, you still get the same result. It's just the same example of that I showed a little bit earlier about the 3D object and its shadow on a piece of paper. If you project once, you get the shadow. If you project the 3D object onto this plane, you get this shadow. If you keep projecting more than once, you'll keep getting the same shadow. So because the projection of this shadow on this plane is the shadow itself. So that is the definition of projection according to linear algebra. Now let's talk about projection a little in depth. All right, so there are different kinds of projection. We have parallel projection and perspective projection. This is the biggest classification, right? The topmost one in the hierarchy. So we have projection, and under that, the first classification, we have parallel and perspective. So what's the differentiation here? This is P, sorry. Perspective. All right, so in parallel projection, parallel lines remain parallel. So if we have, again, a cube, so these lines in a cube are parallel. In parallel projection, after the projection, these lines will still be parallel. In perspective projection, that's not true. Perspective projection is more common in other fields like computer graphics or architecture. Let me show you. So there are different kinds of perspective. Let's clear up the canvas. So here, so this is 1-point perspective. So what's happening? So let me draw a box. Sorry. Okay, it took more time than I thought it would, but you get the picture. So as you can see, if you look closely, we are projecting a 3D cube, right? So the edges of the cube were definitely parallel, but as you can see, this line and this line are not parallel. They were converging at that point. So in one point perspective, as you can see, parallel lines are not parallel after the projection. So this is why it is called perspective projection. This is not important for our course because we are not going to study perspective projection here. But just to give you an idea, there are 2-point perspective. So okay, let me just get this cleared up. So 2-point perspective is similar, but in this case, there are 2 points of convergence. So now neither of these pairs are parallel, nor these pairs are parallel. So if we go from here to 3-point perspective, so now just like before, I'm spending a lot of time drawing. So now as you can see, these are not parallel, these are not parallel, these are not parallel either. Alright, so I think you get a picture of what's happening. Anyway, not important because we are not going to study parallel perspective projection. We are going to study parallel projection. So let's get this removed from here. Alright, so yeah, back to parallel projection. Now, parallel projection can be further divided into 2 types of projection. We have orthogonal or orthographic, and we have oblique. Now, both are parallel projections. What's the difference? So let's say we are trying to project this vector onto this line, right? So if the lines that intersect the projecting surface are perpendicular to the surface, it's called orthogonal. If they are not perpendicular to the surface, then it's called oblique. So let me give you a good example. So let's say this is the ground. Let me bring some colors here. Okay, so this is our ground. All right, now we have some sort of monument here, like so it looks like this. Not a good color. Let's bring pink. All right, so we have some sort of weird monument here. Now a good example of orthogonal projection onto this surface is when the sun is just above and the light rays are coming parallel to the ground. We get the shadow here, right? So this is the shadow. Now this is a very good example of orthogonal projection. Now when the sun is not at top, the sun is coming from here, so our projection is going to be something like this, right? And this angle is obviously not 90 degree and not perpendicular, so this is called oblique projection. And luckily for us or you, we are only going to study orthogonal projection. All right, so I think by now we have a pretty decent idea about what projection is. Pretty like you can feel what projection is, right? So in the future we are going to come up with the formulas, mathematical formulas and definitions and so on. We also know the formal definition of projection in linear algebra. We also saw different kinds of projection. So I hope you got the feel of what we are going to study, I mean projection. So let's move on to the more formal stuff.